Hello, welcome back to my lectures on Introduction to Nuclear Materials for Engineers. Last lecture I talked you through dislocations and diffusion. This lecture we will review precipitates, focusing on steels towards the end of the lecture, before you can begin my main lecture course on nuclear materials. So, what are precipitates? Why do we care? And what do we need to know about them in order for us to get to grips with the main course content? Well, precipitates are of great importance with respect to the strength of materials, as they pin dislocations, which inhibit their motion. However, for precipitates to strengthen a material, they must also be finely dispersed, as if precipitates grow too large, or they coarsen, dislocations can actually move rather easily past them by a mechanism called Austenite bowing, and the strength of the alloy will then decrease. Now, a useful example to show precipitation hardening is that of aluminium copper alloys, such as those used for aircraft. So I'll reference those in your notes on occasion. The figure below here shows a generic phase diagram, and we'll use this as an example here. We can see in this diagram three numbered stages I've identified on the graph. Let's begin at 1. So at 1, we're in the single solid solution alpha phase. Slow cooling down past the solvus line, and that line indicates the limit of solid solubility. As we pass below this line, it's thermodynamically favourable for us to form precipitates, in this case, beta phase. And these precipitates will begin to nucleate below this solvus line at features such as grain boundaries and dislocations. And once nucleated, provided the temperature is sufficient for diffusion, the precipitates will grow until the solute is depleted in the surrounding matrix, reaching the solubility limit. Precipitates may then continue on to coarsen, which is where smaller precipitates dissolve to grow the larger precipitates present, the driving force being the surface energy of the alpha-beta interface in this case. But I'll discuss coarsening later on. Well, let's look at another one. If we went from stage 1, where we're in the alpha phase, and we went straight to stage 2 very rapidly, i.e. the material were quenched. That's what I mean by quench, a very rapid cooling, often in water or oil. Well, if we were to do that quenching, there would be insufficient time at temperature to allow for any precipitation, because precipitation requires diffusion. And that's because the precipitate, because it's a diffusion-dependent phase transformation, without time at temperature, you can't form those precipitates, because the atoms don't have time to move about to form the precipitates in the first place. You could quench the material, however, and then reheat it from stage 2, so after this quench, you could then reheat it to stage 3 and precipitate fine precipitates upon that reheating. Okay? Basically what that would do is, when you quench to room temperature, you maintain the solid solution. So you leave a supersaturated population of vacancies, as you essentially retain the equilibrium population of vacancies at the temperature you quenched from, at complete solid solution, i.e. stage 1. And the excess quenched in vacancies help in the subsequent aging of the alloy when we go up to reheat it. When you reheat the material or age the material at a slightly elevated temperature below the solvus temperature, you can form a sequence of metastable precipitates. And those metastable precipitates would eventually produce the equilibrium beta phase if you gave it sufficient time to grow. Okay? So, I've spoken about precipitates not in much detail over these introductory lectures, but I have mentioned previously that they're an effective method of strengthening, with the sort of optimum heat treatment being one which results in a population of metastable precipitates which are just beyond peak hardness. So to induce plastic deformation, as dislocations have to bow around these metastable precipitates by bowing, rather than being able to cut through the precipitates. Now let's look at the kinetics of precipitation. First, our first stage is nucleation. Well, how does a precipitate nucleate? They nucleate through thermal fluctuations, such as localized temperature spikes, creating embryos of the precipitate phase that, should they reach a critical radius in size, can become stable and grow. And this critical radius is represented by the R star on this figure at the top of page 39. And that's showing the point where the Gibbs free energy begins to reduce with increasing precipitate size. Okay? The Gibbs free energy is the driving force here, and that depends on undercooling. However, this driving force is opposed by the strain energy. Should the volume of the new phase be different to that of the parent matrix, shown on the left curve of the graph, and is also opposed by the surface energy, which itself depends on the coherency of the precipitate matrix interface. And we can derive that delta G for nucleation mathematically, as I've shown here towards the bottom of the page, okay, for our delta Gn. And should we differentiate this equation with respect to precipitate radius, we see that when strain energy equals naught, the critical values of delta G and radius for a stable spherical nucleus are as follows for our R star and our delta G star. Okay? Now before we move on, there's one final point to raise relating to surface energy specifically. You'll find that metastable precipitates form prior to the equilibrium precipitates. And that's because those metastable precipitates form more readily as an intermediate stage because they're more coherent. So that coherency in the strain energy, because of that, makes it more favourable to form those metastable precipitates that eventually will form equilibrium precipitates. So because they're more coherent, their delta G is lower, their delta G star rather is lower, so that means that they're more favourable to form. Okay. Now let's move on and take a look at steels specifically. Back in lecture 1, I believe, I discussed the basics of mechanical properties and the challenges surrounding the design of a high strength, high toughness material. Toughness being resistance to cracking, strength being resistance to plastic deformation. And you may recall that in general, the toughness of a material decreases as its strength increases, as a result of the reduced plasticity at a crack tip. And that reduced plasticity at the crack tip limits the energy that can be absorbed prior to failure. And if you look at the figure here below, you see the range of toughness and yield stresses for different types of materials. Pure materials are typically very tough, but their yield stresses are far too low for most engineering applications. Mild steel, on the other hand, with carbon contents of up to 0.2 weight% carbon, is very popular. I mean, it's ductile, it's tough, it's machinable, it's weldable, and often most importantly, it's affordable, with a yield stress adaptable to a wide range of engineering applications, from precipitate strengthening and solid solution strengthening, is how you can change that yield stress to accommodate its intended application. And there are a lot of different steels available with a wide range of properties. There are Martensitic low alloy steels, which can then be tempered to provide some ductility and toughness, and I'll talk about that. Mar-aging steels, which contain no carbon but form martensite and are then aged. And last but not least, trip steels, transformation-induced plasticity steels. And that's where crack growth causes martensite at the tip of the crack, which increases toughness. So you've got a lot of steels to choose from. And I've given you the iron-carbon phase diagram here on page 41 for reference. Okay, just for reference purposes. But as I said, that there's a wide range of steels of complex microstructures with yield stresses ranging from the tens to the thousands of megapascals. Now here, on page 42 at the top, I've provided you some general guidance on composition of the categories of steels, should you ever need to refer back come my main lecture materials course. But what we'll finish off with today is the thermodynamics and kinetics in these kind of steels. Something you may see from time to time are things called Ttt graphs or diagrams, and they are time temperature transformation curves, and these show the degree of transformation that a steel may undergo at a given temperature for a given time. As you dope a steel with additional solutes, the stability of different phases may change, altering the driving forces for their formation and changing the Tt curves. And that's because some of the solutes will prefer to exist in one phase rather than another, and so will partition during the transformation. So let's have an example. Take austenite transformation to ferrite to cementite. Yeah, so we've got pure austenite and we're transforming to ferrite and cementite. Remember, cementite is iron carbide, so that's a precipitate, whereas ferrite is a new matrix phase. Well, partitioning requires diffusion, and this will occur at the growing interface. Now, carbon is an interstitial, both in ferrite and austenite, and so it diffuses very quickly because it can travel through the interstitial sites. But other alloying additions are substitutional. Other alloying additions are substitution in the iron lattice, and so will diffuse much slower, limiting transformation rate. So look at this figure at the bottom of page 42 here. You can see the lamellae of ferrite and cementite forming from the prior austenite. Here, carbon is partitioning to the cementite, and alloying additions such as silicon are being partitioned into the ferrite out of the cementite regions. Okay, and that's because silicon is a substitutional atom, and it significantly reduces the cementite growth rate because the cementite doesn't want silicon in it, so it pushes it out. And so in order to grow cementite, it needs to repel this silicon, so it delays the formation of cementite. And that would shift the Tt curves to later times. So that's what I'm talking about, partitioning, and how you can influence with composition, influence the rate of transformation. Okay, and that's why Ttt curves are quite useful. Now, I've mentioned Martensite already today on a number of occasions, but I've not really discussed, its formation. And Martensite is rather unique in that its formation is formed by something called a displacive shear transformation, and that does not require any diffusion. Now, Martensite is a non-equilibrium phase, and it forms because we quench steels from austenite very quickly down to the Martensite start temperature. And because we quench it very quickly, there's no time for carbon to diffuse to form cementite, our iron carbide. So the carbon remains in supersaturated solid solution in a body-centered tetragonal lattice. So remember, ferrite is body-centered, while Martensite is tetragonal body-centered. So A equals B but doesn't equal C in terms of the lattice parameters. And it has a high internal strain energy. the martensite. And that means that said martensite is very hard and very brittle. And this hardness will increase the greater the carbon concentration. And that's why we temper martensite. Because in tempering, which is heating up to a slightly raised temperature, tempering allows some ductility and toughness, and it allows some precipitate formation, which retains some of the hardness as the martensite decomposes. You're not going to retain anywhere near the hardness of the fresh martensite, but you get some of the ductility and toughness that you will want while retaining some reasonable hardness. And that's what tempered martensite is. It's decomposed martensite where you formed some temper carbides that form upon tempering. And that's martensite. And in turn, that, my friends, is the end of our introductory course lectures. You'll find 2 appendices and a glossary for reference during my main nuclear materials lecture course. Appendix 1 gives the crystal structures of materials that we're going to look at in nuclear power, or rather the most important ones in nuclear power generation. Again, that's just for your reference from when you're going through the main course, to give you a hand. Appendix 2, this discusses the 4 index notation, which is used in hexagonal and trigonal systems. Although I don't use this in my lecture course apart from briefly for zirconium cladding, it may prove useful to you later, should you continue working on materials challenges in your future studies or professional careers. It's worth having a sort of little Bible for you, which I hope this course provides. And the last thing would be, you've done question sheet 1, you can do question sheet 2 now, which is at the end of your notes. Okay, and that covers the second half of these introductory lectures, including any diffusion, dislocation, microstructure, and phase diagrams. Should you have any issues, once again, let me know by sending me a message or leaving a comment, and I'll do my best to get back to you as soon as possible. But I hope these lectures have proved useful, and I'll see you shortly to begin my main nuclear materials lecture course. So, all the best. See you then.